Okay, welcome back from spring break, or for some of you, you might actually be watching this during spring break. I hope everybody's staying safe and healthy and sane. This is a crazy time. So if I can do anything to help you out, don't hesitate to let me know what you need. I realize this is really tough to transition to an online class with very little warning. Okay, but we're going to do it. So we're looking at 15.3, which is integration in polar coordinates. Okay, for this, we are going to require that r be bigger than or equal to 0. So in general, in polar coordinates, r can be anything, theta can be anything, as long as you pair them up appropriately. When we're integrating, r must be bigger than or equal to 0, and you need to make sure that you set up all of your integrals so that that's true. Okay. We're going to be working with what's called a simple polar region. Simple polar region. The book doesn't actually use that terminology. The vocabulary isn't super important. The concept is. So we're going to have a region D, which is described in polar coordinates as the set of all points r, theta, such that r1 of theta is less than or equal to r2. Is less than or equal to r, which is less than or equal to r2 of theta, and alpha is less than or equal to theta is less than or equal to beta, where beta minus alpha is less than or equal to 2 pi. Oh my goodness, what does that mean? Okay, well, here's all it means. We're going to have two boundary curves. An inner one, which I'm calling r1 of theta, and an outer one, which I'm calling r2 of theta. And we're going to have two boundary rays. Now, ordinarily, when theta is constant, that gives us a line. Theta being constant with r being non-negative is going to give us a ray. So let's say this is the ray, theta equals alpha. And let's say this is the ray, theta equals beta. Okay. So I've got these two theta boundaries that are these rays. The rule is that the difference between beta and alpha has to be less than or equal to 2 pi. That's just saying you can't go around and repeat the region. You can only count the region once. Okay. And then defined on this interval of theta values, I'm going to have an inner r boundary, which we'll call r1 of theta, and an outer boundary, which we'll call r2 of theta. And we're talking about the region that's enclosed by that. So it's the usual thing that we have four boundaries, two theta boundaries and two r boundaries. And we're also having it so that two of them are constant and two of them are allowed to be continuous functions. In theory, it would be possible to have constant r values and have theta as a function of r. We're just not going to see it this semester. It is so much simpler if we have r as a function of theta than theta as a function of r. If you just think about comparing trig to inverse trig, r is a function, you've got functions of your angle theta. Inverse trig, the angle is the output of the function. So we're going to be working with regions something like this. And we're going to be trying to, if we have such a region, we're going to be trying to evaluate the double integral over that region D of f of xy dA. Now, I know how to convert the integrand into polar coordinates because I know that x is just r cosine theta, and y is just r sine theta. But what we're going to need to do is figure out how do we write the dA in terms of polar coordinates. Okay, so for doing that, we are going to go through our usual four-step process, which is that we are going to chop things up into little pieces, and then we're going to approximate the signed volume over each piece. We're going to add them all up. We're going to call that a Riemann sum, and we're going to take the limit of that piece, of that sum rather. Okay, so step one is to chop. Now, when we're working in rectangular coordinates, we chop things into little rectangles. When we're working in polar coordinates, we're going to chop things into what are called polar rectangles. So, if this was my region D that I was working with, a polar rectangle is just something that's bounded by 4 constant functions, but in polar coordinates. So this is going to be bounded by 2 circles, r equals r1 and r equals r2, and 2 rays, theta equals theta1 and theta equals theta2. So I'm basically saying, okay, let's draw a bunch of constant theta rays here. That divides this up into wedges. And then let's also draw a bunch of constant r curves. That would just be circles centered at the origin. Okay. So that each one of these things is what we call a polar rectangle. It's bounded by 2 circles and 2 rays. So this would essentially be my r equals r1, r equals r2, theta equals theta1, and theta equals theta2 for my lovely polar rectangle. Okay. Now, of course, I'm chopping my region up into a bunch of pieces. Interesting thing shows up here, which is that my simple polar region might not fit perfectly when I chop it up into a bunch of polar rectangles. You can sort of see there's this little patch of area right here that is part of this polar rectangle, but was not part of the original thing, because this was my original boundary for my region D. So this polar rectangle contains some area that's in D and some area that's not in D. Now, if I'm chopping things finer and finer, the number of polar rectangles where that happens is maybe going to increase, but the region that's included in that is going to be decreasing and going to 0. So what we usually do is, if I have something like this, I can just say, I'm going to extend the domain of my function to include this area here, but I'm just going to define the function to take on a value of 0 if it's outside of the region D, but inside of the polar rectangles into which I've chopped things. And so then when I choose my representative point to choose a representative height, if I choose a point in D, the representative height is the function value there. If I choose a point that was outside of D, the representative height is just 0. Okay, so that's how we're going to deal with that. I'm also going to introduce, for the r values and for the theta values, I'm going to have both the index to keep track of my chopping and the number of pieces. So with r, I'm going to have an index of I, and I'm going to chop into m pieces. With theta, I'm going to have an index of j, and I'm going to chop into n pieces. This is just to help us in setting up our Riemann sum. Okay, so basically I is a variable. It counts from 1 to m, where m is the number of circles that I've drawn in creating these polar rectangles, and j is an index, a variable taking on positive integer values that goes from 1 to n, where n is the number of rays I've used in chopping this up into polar rectangles. Okay, so we have chopped things into polar rectangles. So step 2 then is to approximate the signed volume that we have over each polar rectangle. Okay, so let me clear some space on the board here. I think I'm actually going to stop this video and pick up with step 2 in the next video, because we've been going for about 10 minutes here. So we'll come back with step 2 in the next video. See you then.